All right, good morning, everyone. We talked last week about how we generate code for Nock, or how we linearize the code, since Nock programs, like most other programs, are trees. And in order to generate machine code, we need to sort of lay everything out in a straight line. We talked a little bit about, but kind of left unsolved, the issue of the dynamic nature of Nock, and in particular how Nock code invokes other Nock code. This is how Nock does recursion. This is how Nock calls library functions. This is how Nock invokes other components of the system, also written in Nock. So this is how Arvo invokes vanes. This is how vanes run. This is how Gall, which is a vane, invokes user space agents. So this is something we really need to be able to support for all these reasons. And yeah, we're going to have a little bit of difficulty with this. To see why, let's take a look at the Nock specification again. So this is Nock. We have the definition of a noun. We have all the meta operations that we use to define Nock that we talked about before. We have cell test, we have increment, we have tree addressing and tree editing, and then we have the definition of all 13 Nock operations. But let's focus in just on Nock 2 for a second. So Nock 2 is sort of the basic base layer way that Nock code can invoke other Nock code. So the definition's quite simple. It says we have two subformulas. That's the meta variables b and c. We're going to evaluate the formula in meta variable b against the meta variable a, which is the subject, all the way through the Nock spec. We're then going to evaluate meta variable c against the subject in meta variable a. Then we're going, but if we look at where these evaluations are placed, what this means is we're then going to take that result from evaluating meta variable b, make that the subject, and the result of meta variable c, the noun that comes back that we compute from meta variable c, will be the formula. We'll run that computed formula against that computed subject, and whatever that result is the result of Nock 2. Let's take a look at Nock 9 for a second. So Nock 9, we notice, is defined in terms of Nock 2. So we'll compute the subject from C, like before, and then we'll run Nock 2, where the computation for the subject is very simple. It's just take the subject as is. 0, 1 means take the whole subject, and putting it there means we're going to use the subject. And then that 0b in there is saying we're going to take some axis out of the new subject and use that as our formula. So Nock 9 is a little bit more restricted. We compute a subject, and then some piece of that subject becomes our formula, not some arbitrary other computation. But again, we did some arbitrary computation to come up with that new subject. In general, we would say this is a core, although the Hoon definition of a core, if you're familiar with that, is slightly more restrictive, because Nock 9 can index in anywhere in this subject, and in Hoon it would have to live under axis 2 in the head of this new subject. So once again, we have this issue that the code we invoke is the result of some arbitrary computation. You get close to this in functional languages, lambda languages, but that code is still written down somewhere and called as a label. Even if you have a lambda that you returned from somewhere, that code is still written in line, and the dynamic part is just the closure, just the data. So you can lift all lambda definitions out to globals and parameterize them. That won't work here, because we could literally produce any arbitrary code. So this isn't beta reduction, this isn't procedure calls. This is, if you're familiar with JavaScript or Lisp, this is eval. We take arbitrary computation results and treat them as new code. So if you're familiar with JavaScript or Lisp, you'll know that you're generally encouraged not to use eval. Perhaps more so in Lisp than in JavaScript. Certainly in JavaScript, you're basically told never to use eval because, first of all, it's a security risk. Any arbitrary code from your user form could be run in your web page. But more specifically, it's also slow because JavaScript can't ahead of time predict what code is going to result there. So you're going to have to parse that string, or in our case, that noun. You're going to have to interpret it or generate code for it. And that's all going to take some time. So you'd rather just do a procedure call if at all possible. But in Nock, again, we don't have anything that's actually a procedure call. So in order to generate, and remember we use this even for library function calls. We use this anytime we call add, anytime we call decrement, anytime we call turn on a list, anytime we call need on a unit value to assert that it's actually inhabited. Anytime we call an arm of a core in Hoon, that's a Nock 9. Which means that for your average library function invocation, you actually do 2 of these because you do one to evaluate the arm of the core. So that's just evaluating that name. When you evaluate the name add, that's an arm in your subject. And that runs a Nock 9 to go and get that. It's generally a fairly trivial one, but nonetheless, that's what it is. And then you will run a second Nock 9 on the result of that, with a Nock 10 in between to put in the parameters for the gate invocation. So if you're calling add, you'll have one Nock 9 to get the actual gate for add, and then you'll have a second Nock 9 with a nested Nock 10 to edit in to the core for add the 2 parameters that you're going to run. So this means that we need to have some way of turning these into what we call direct calls or direct jumps. The best we can do, if we just naively treat this as eval, is cache generated code, try to come up with some scheme to make our cache keys match even if our parameters are different, and then do what we call an indirect jump, meaning that we have to tell the CPU at runtime, have it load from a register the instruction pointer that it's going to call or jump to. What we'd like to do is actually not have to cache anything, just have all the code generated ahead of time, put a label on it, and do a direct call or jump where the label, which gets turned into an instruction pointer, is actually in the instruction stream of the assembly code or the machine code. So how are we going to do that? We're going to need some way to predict what formula is going to come out of this core, or if we look at both Nock 2 or Nock 9, we need some way to predict what formula winds up here at the end here where we compute the formula, and some further knowledge about what's in the subject, because the semantics of a formula can vary drastically depending on what's in the subject. So the add gate depends on not only itself, but also the decrement gate being at specific places in its subject, because that's how it recurs on itself and that's how it decrements for the naive invocation of add. Of course, in practice, we actually jet add, but still, even to be able to define add, we have to be able to write it this way. And to invoke add, to write a function that invokes add, that needs to be needs to have the add gate at a particular place in the subject. So the answer to this is something it seems straightforward, but actually took several months to convince myself that this would actually work once I decided it was even reasonable to look into it. And that is something that I call subject knowledge analysis. So subject knowledge analysis is just simply starting with some partial knowledge of a noun, the subject is just a noun, as an assumption about what we will have as the subject for a formula, and then using that to predict some partial knowledge of what the result of the formula will be. And by propagating these predictions through as we generate code, we can always check whether we can reliably, safely predict what formula we're going to invoke for a Nock 2 or a Nock 9, and then generate code for it and insert a direct call if that formula is not in tail position, or a direct jump if it is. So this partial knowledge looks like this. The sock type is just a partial noun type. In the default case, you know nothing about the noun. It could be an atom, it could be a cell. If it's an atom, it could be any atom. If it's a cell, it could have arbitrary head and tail. We might know that it's an atom, but know nothing about which atom. More specifically, we might know that it's a lubine, and there's a particular reason for pulling this out, which is that knowing whether something will crash or not in Nock often depends on knowing that a noun is a lubine. For those of you who might not be familiar with the term, lubine is the Urbit term for the sort of flipped Boolean that Nock uses, where 0 encodes truth and 1 encodes falsity, which is the opposite of the Terran convention. We might know that it's a cell, and then recursively know something about its head and its tail. And finally, we might just actually know what it is. We might know that it's an atom and which atom, or we might know that it's a cell and recursively what its contents are. So note that the only recursive case here that doesn't just have a full noun in place is the cell case. So we could know more about the head than the tail. We could know more about the tail than the head. We might know nothing about either of them and just know that this is a cell. But here the tree structure of nouns really helps us because it's very straightforward to derive this sort of partial structure of a noun. One more thing we're going to want to keep track of is what we know about whether or not computation will crash. So in particular, fetching an invalid access out of a noun can crash. Having a non-lubine as the result of the test expression of Nock 6, the if-then-else for Nock, can crash. Trying to increment a cell, Nock 4, a cell can crash. A few other cases, but if you have subformulas and one of those subformulas crashes, then your formula also crashes. One subtle case of this, or somewhat subtle case of this, that the Nock documentation calls out is that if you have a dynamic hint, if we look at Nock, it's the more involved case of Nock 11, which I don't have a slide ready to highlight for you, I'm sorry. If the hint whose result we throw away crashes, the computation crashes, even if the hinted formula that actually produces the result would not crash. So just something to remember about if any subformula crashes, then your Nock computation crashes. And so it's incorrect for an interpreter or a compiler to throw away Nock code that might crash. So it's important for us to keep track of this safety information. So we have 3 cases. 2 of them wrap around a sock because it could return something. So the safe case means the computation that produced this result that we're predicting will not crash. Risk means the computation that produced this result might crash, but if it does not, it will return this result. This can happen if we don't know enough about the subject or the result of the core subformula in a 9 to know that the axis will be valid, or about the outer tree that's being edited in a Nock 10. This can happen if you have a conditional and one side crashes and the other doesn't, and you don't know enough to know which branch of the conditional you'll take. A couple other places where this can happen. Again, this can also happen if any subformula of yours might crash, then you also might crash. And then the last case is we know that this will crash. For instance, if we try to analyze 0 of 0, we know this will crash. Or if we try to analyze 0 of 2, but we know that the subject is an atom, we know that that will crash. So this lets us propagate safety information, which in a code generation setting is mandatory to let us know that we can drop code. So in particular, when we do procedure calls, we want to have jumps into the procedure, but without knowing that the code that produces the formula will not crash, we still have to run that code that produces the formula, even though we already know what the formula will be. Otherwise, we might have incorrect semantics. If we know that it won't crash, then we simply do not need to run the code because we already know its result. And in particular, anywhere where we fully know a result and we know that it will not crash, you could replace that computation by just an immediate of the noun you already know it will produce, and that would be correct semantically. So what does this actually look like? We're not going to go over this as it is integrated into the code generator. We'll probably do that in another stream, or at least call that out. But this is a function that just does subject knowledge analysis without code generation. So it takes some assumption about a subject, it takes a formula, and it produces a boot type, which says what we know about whether it will crash, and if it might not crash or will not crash, what we know about its result. So starting straight off, we pattern match on the formula using a whatless, and this entry in the whatless is the default. So the default is if it's not valid Nock, then it will crash. And this is the very last case in the spec. If we look at the very last line in the spec, anything not matched goes into an infinite loop, which is equivalent to a crash in Nock. The first valid case is the autocons case, where you run 2 formulas together and produce a pair. And very simply, we recursively analyze each formula without altering the subject. And then these helper functions are defined as helpers because then we can use them to help us propagate subject knowledge information in the actual code generator. But this one simply creates a pair, checks how much we know to see whether it needs to generate the no case or the bets case of a sock. Do we fully know both sides that we can say no? Otherwise, we need to say bets because we have partial knowledge on one side or the other. And also checks their safety information. So if either of these crashes, it will also spit out the boom case to record a crash. If they're both safe, then it will also be safe. But if either of them is the risk case, meaning it might crash, then the whole thing is the risk case. So that's fairly straightforward. 0 is similarly straightforward. Poll goes through a sock. So we'll take the subject sock and takes an axis and tries to decide what we know about the result. If we know enough about the result, if we know that there's enough cells on the way down for the axis that's recorded here, then it's safe. So these can be the no case of cells, or this can be the bets case, which says we know it's a cell, we just don't know everything about what's underneath. And if we have enough of this to exhaust the axis and get to 1, then we can just produce whatever subject knowledge we remain with as the result. If we get to the guess case saying we don't know, then this will return guess as the result sock, but it will be returned as a risk case because we don't know that the axis will be valid. If it gets to an atom case, the dice case or the flip case, and there's still bits remaining in the axis, if it's not axis 1 anymore, then it will produce a crash. So again, fairly straightforward, does what you expect. It just has to keep track of the safety information as well as what we can know about what axis we can pull out of the subject. The 1 case, even more trivial. It's a constant. 1 won't crash, so we know it's safe. We know the result because it's written right down there, and so we'll just give that back and say, we know this won't crash and we know what it'll produce. 2, on the other hand, is not so straightforward. So first of all, and this specification documentation function is actually incomplete because I have not actually pushed this table down through. What should happen is on entry before we start our pattern match, we should check whether we've already seen this formula with this subject in this map, and if so, just return whatever's written down there. And when we go to enter a formula, we should, if it's not already in the map, then we should insert what we call a black hole. We should say, we don't know whether this will crash or not, so risk. We don't know what it will return because we're in the process of analyzing it. So if you recursively call it, then you know nothing about what the recursive call will produce. For those of you who have some understanding of programming languages, implementation, and compiler analyses in particular, this is what differentiates subject knowledge analysis from something like data flow analysis. The data flow analysis will actually do a fixed point algorithm to try to saturate what we can know about the data flow in a particular case. We're not trying to do a generalized data flow. We're just trying to make sure we have enough information to know what formulas we will run. And in general, we're not getting formulas out of the results of recursive functions. There's a couple cases where we might be that would require some special handling through hints, but in general, we're not trying to do that. And so we will just refuse to analyze recursion and just say we know nothing about it, and that's fine. But going on, we're going to first just analyze the subject formula, short circuit with a crash if it crashes, analyze the formula for the formula, and again short circuit if it crashes. If we got atom knowledge out of a formula, we're going to crash because the formula can't be an atom. So it's just another short circuit to get some cases out of our pattern match. If we don't know what formula will come back, so we'll check a couple cases here, but by default then, if we don't know what formula will come back, we will say we don't know if it will crash, we don't know what it produces, because we don't know what it is. If we know what it is, and we know that the computation won't crash, and we know that the subject computation will also not crash, then we can say the whole computation won't crash, and here's what we know about what it will return. Obviously, the formula itself could still be a formula that might crash, but this, we don't have to further edit the safety information. If the subject computation could crash, then our whole computation could crash. So this dir function is a helper that will not allow safety information to come back as safe. If it comes back as crash, it'll be crash. If it comes back as safe or risk, it will be turned into risk. In this particular case, in a code generator, this would be handled specially because this is the case where we could throw away the code to evaluate the formula for the formula. We can simply throw it away because we know what it will generate, we know it won't crash, and so we actually don't need it at all. We're just going to generate a label to code that we generated for that result formula and go there. In all of these other cases, we're still going to need to run the formula because it might crash. And if we actually don't know what formula, we're still going to have to run it and then branch back to our code generator or to an interpreter and evaluate the formula. So that's Nock 2. And it's not as hard as it looks. It's just a lot of cases to consider and some subtleties around crash semantics. Nock 3 is more straightforward. The helper function here will return knowledge of 0 if we know that this, we don't have to know everything about this. It could be the bets case, but if we get the bets case or the no case of a cell, then we know that this will return a cell, and so it will return knowledge of a cell. The only way that it will crash or possibly crash is if the subformula crashes or possibly crashes. There's no invalid intermediate result for 3. If we know that this is an atom, so if we get the dice case or the flip case back or knowledge of an atom, then it will return knowledge of 1. And if it has guess, meaning we actually don't know anything about the noun, it could be a cell or an atom, then it will return the flip case because we know that 3 will always return a loopy. 4 is also a little bit subtle because remember that the goal of this is not to maximize our knowledge. The goal of this is to produce knowledge that helps us toward a specific goal, which is predicting and labeling code that we will jump to. So 4 will again propagate safety information. It will produce knowledge of a crash if we know that this is not an atom. But if we know that this is an atom, it will produce the dice case of knowledge. It will, if you know which atom, it will not produce no of the atom's increment. And this is to avoid generating a whole sequence of labels in the case of if you know one of your arguments to add, for instance, and you didn't do this, then you would actually unroll the add loop for that particular case all the way down, which would makes jet matching harder, unnecessarily fills up your code table. We just really don't want to do that. We aren't going to use 4 to generate a formula if we're writing sensible Hoon, and so that's just not something we need to write down knowledge about. Nock 5 is our equality test, so we're going to see what we know. If we don't know everything about either of these, then we're going to return flip again. We know this result will be a looping, we don't know which looping. If we know both of them completely and they're equal, we know that we'll return 0. If we know them both completely and know that they're disequal, then we can return 1. We could actually be a little bit more involved about this, but again, for similar reasons to 4, it's not really worth taking care of the subtle case where we partially know enough to know that they're disequal. We could do that. It's might be worthwhile to help with specializing pattern matches, for instance, but I don't think you need to do that to specialize pattern matches. But in any case, if we do know that two things that were tested for equality are equal, then we can return knowledge of 0. And this is helpful along with 3. 3 and 5 are Nock generated for type matches. This is helpful because for Nock 6, we can actually look at what we know about the result of the conditional. So again, we'll evaluate the conditional first, the test. If it crashes, then we will crash, or if it doesn't return something useful, we will crash. So if we get bets, or if we get knowledge of a cell, or we get knowledge of a non-looping atom, we're going to crash. There's all sorts of ways. There's all sorts of wrong things we could return in a test branch that would make us crash. But if we know that the result is 0, then we can just analyze the true branch of 6, so this second subformula here. If we know that it's 1, we can just analyze the false branch, which is this third subformula here. This is for when we know that the conditional won't crash, so the crash safety is just dependent on which subformula we know we're going to run. If we know that it's a looping, then we can intersect what we know about both subjects. So we can say we know all the places where they agree, and where one of them doesn't know, or where they disagree, then we have to say we don't know. Because we don't have enough information to predict which branch we're going to take, so we don't know what the result will be unless both branches agree on the result. In these other two cases, we actually don't know enough to know that it will be a looping returning. It could be in both of these cases. So we're going to say, here's the result intersected like before, but also we might crash. And then the case where the test itself might crash is similar, except we have to annotate all of these to say they might crash. In particular, in this case and this case, where it's safe and where you know the result, you can actually throw away the conditional entirely when you're generating code. You can throw away the test case and just generate code for these directly. This combined with 5 and 3 should, in many cases, get you specialization for gates that do a pattern match on their input. If you call the gate with a particular instance of a tagged union that's written down in the code, you should be able to know that that's the tag that you're calling it with, and generate a specialized version of the code for a gate that just runs that branch of the pattern match. So that's a pretty neat side effect that we get quite nicely out of this. Nock 7, 8, and 9 are the cases, aside from 2, where we're really going to start messing with the subject. So for 7, we're just going to compute the new subject. If we get it back safely, we can just see what happens when we evaluate the formula. If we get it back, but it might crash, then we can check we can see what happens, but we have to say, well, we might crash as well. Again, the invocation of dare. And then for any other case, notably for the crash case, this will also crash. 8 is very similar, except we're going to cons the subject. So nit is like cob that we saw for the autocons case above, except since it's the subject, there's not safety information. We don't pass safety information in about the subject. We get safety information out. So we're examining the safety information here in order to properly return safety information for our whole computation, but we're not passing safety information in the subject. It only flows out, not in. So nit is to cons to socks, cob is to cons to boots. And then Nock 9 has a very similar look to Nock 2, except instead of evaluating another formula to get the formula, we're using pull, like we used from Nock 0, to look at the result of the subject producing computation and get the specified access out of it. It's otherwise essentially the same code. Nock 10, there's a helper to properly propagate the safety information. It's a little tricky, but this is just patching in what we know about the patch and what we know about the whole tree, and checking the access and making sure that's valid and properly propagating all that safety information. For Nock 11, which is a hint, if it's a static hint, meaning the hint is just an atom, there's no extra code to evaluate, so we're just going to evaluate the subcomputation. For the dynamic hint, we have to look at, this should be @tar, actually. We're going to look at the hint computation first and analyze it. We're going to crash if it crashes. If it's safe, we're just going to analyze the other computation. And again, in this case, in a code generator, we could throw away the code for the dynamic hint and just produce the code for the subcomputation, because the only effect that the hint can have on the semantics of the computation is to crash it. And if it doesn't crash it, it will have no effect on the result of the computation. So it would be safe to throw away. If the hint could crash, then we have to say, well, this might also crash as well. And in a code generator, we actually have to produce code to run the hint to see if it will crash. And then for, we have a case for Nock 12, because if we're writing a code generator, we're going to have to handle Nock 12. Nock 12 is a fake opcode that only exists in virtual Nock, that is, Nock interpreted by Nock. But since we jet that with the underlying interpreter in a reasonable runtime, the interpreter has to know how to handle it. And this is the scry operation, .cat. And whatever comes in Nock 12, we're not going to try to analyze it. We have no idea what our virtual environment might put there. So we're just going to say, we don't know if it will crash. We don't have enough information to know if a scry path is valid, so it might crash. And we have no idea what it will return either. So that's it. That's all of subject knowledge analysis. If we go take a look at the code generator that we looked at last week, I'm actually working on rewriting this right now, but this is what we looked at last week. We can see, for instance, when we generate code for an autocons computation, when we recursively call code generator on the subcomputations, we get back information about what we know from those subcomputations, and we use that same helper function cob to return what we know about this computation. Similarly, for 0, we use that pull function that we saw. If we look at 2 now, we can see, again, checking whether a computation produces a crash and short-circuiting. This bomb helper is not just producing knowledge of a crash, but is actually writing down in the IR an instruction that says, actually, this just crashes. So hopefully this gives you an idea of what subject knowledge analysis is and how it helps us generate the kind of code that we'd like to generate if we are ahead of time compiling Nock in order to run it. If you have any questions, feel free to ping me in the new Mars group. One thing, real quick before I go, I'd love to be able to have comments in the new Mars group pop up and be able to highlight them in the stream, but Urbit isn't supported by StreamYard, and OBS doesn't seem to have this functionality at all. So if someone is interested in helping to build this functionality to tie OBS to an Urbit so it can present messages from a chat and highlight them on a screen, please get in touch with me. It's something I'd be really interested in seeing built. So that's all. I hope this was helpful, and I'll see you on